Part A of FRQ1 asks to draw and label the forces acting on the block for the incline segment. For the incline, you have the block M going down the ramp, and you know that you have the force F of G, which is the force of gravity going down, and then you also have normal force acting against F of G. Then we also have the force of kinetic friction acting against the block, F of K. Then for part B, you have to find the angle of the ramp. We could find that by doing the net force, which equals mass times acceleration. The net force would be F of X, which is the force of gravity in the X direction, minus F of K, which would equal mass times acceleration. F of X, we know, is mg sine theta minus F of K, which would be found in mu K equals Fk over Fn. Mu K times Fn equals F of K. So mg sine theta minus mg cosine theta, which is Fn times mu K, equals mass times acceleration. Mass times acceleration equals 0, because we know that A is 0, has the velocity is constant, which we can see from the x of t graph being a straight diagonal line. So mg sine theta minus mg cosine theta equals 0. We know that mg sine theta can equal mg cosine theta times mu K. Then if we cancel out mg on both sides, we get sine theta equals cosine theta times mu K. We can divide both sides by cosine. Sine over cosine is tangent, which would equal mu K. If we do inverse of tangent, mu K, we would find our angle. And the tangent inverse of 0.3, which is our mu K, would be 16.7 degrees. That's our angle. And then part C asks to calculate the coefficient of friction mu on the horizontal flat segment, which you could find by doing mu, which is equal to Fk over Fn. We know that net force equals mass times acceleration, where net force is Fk, mass times acceleration, and Fn, we know the absolute value would just be mass times gravity. We can replace those values in our given formula. Fn can be replaced with ma, or Fk can be replaced with mass times acceleration, and Fn can be replaced with mass times gravity. Mu equals a over g when you've canceled out the mass. From there, you can find acceleration from our given graphs. V average is the change in x over change in t. V average would be 10 over 5 given in the graph. V average equals 2. Then we also know that it is Vf plus Vi over 2. It would be 0 plus Vf over 2 equal to 2. Multiply by 2 on both sides to get 0 plus Vf equals 4. Vf would just equal 4 meters per second. And we can do that. Mu equals 4. not 4, because we still have to find our A, which is change in V over change in T. A equals 0 minus 4, because that's our change in V, over change in T would be 5 seconds, which is 0.8 negative. So our value for A would be 0.8 over negative 9.8. They're both negative, which would cancel out. So then mu would equal 0.8 over 9.8, which is about 0.082. Part D is asking how much distance is needed to bring the block to a complete stop during the flat segment. In order to do that, we first have to find the total time it takes to reach a complete stop, and we can do that by setting VF, which we would set as 0, equal to AT plus VI. A, we have already determined, is negative 0.8, T plus VI, which would be 4, because that's the velocity at the end of the incline. So 0 equals negative 0.8 T plus 4. We put 4 on the other side, times T. You divide by 0.8, cancel it out on that side, negative 4 over negative 0.8, negative cancels out, equals T. T would just equal 5. So that's the time it takes to come to a complete stop. And then we could just use the time it takes to plug into the formula. Change in x equals VIT plus 1/2 a t squared. Change in x equals VI 4 plus t 5 plus 1/2 0.8 negative t squared. Change in x now equals 20 plus negative 0.4 times 25. Change in x equals 20 minus 10. Change in x equals 10. It's part D. And then part E is asking to calculate the block's average speed during the horizontal flat segment. Speed average would be the change in x over change in t. Change in x is 10, t is 5. So your speed would just be 2 meters per second. Then part E is asking to sketch the shapes of the corresponding x of t and a of t graphs for the horizontal flat segment. So for part F, our x of t graph would be one, 2, 3, 4, 5, 2, 3, 4, 5 x t. It would just be an upward curved line as our velocity changes. A is not constant, and then it is decreasing as time is passing. And then our a of t graph would be a constant straight line at 0.8. Then part G says if the distance of the horizontal segment is shortened to d over 3 and the system is raised to 10 meters above the ground as shown above, how far, distance x, from the base would the block land? For that, we would start by finding our VF at the edge of the block. So we would do change in x equals VF squared minus VI squared over 2a. Our original distance D was 10. We divide that by 3 because that's our new distance between the end of the incline to the edge of the cliff. You would get that to equal VF squared minus 4, which is our ending velocity there, squared, over 2 times negative 0.8. Would get, to solve for VF squared, you would do 10 over 3 times 2 times negative 1.6, because that's 2 times 0.8, equal to VF squared minus 16. 10 divided by 3 times negative 1.6 plus 16 equals VF squared. Cancel out the square root the other side. Get VF equals that value, which would be about 4.62. Which is our VF. And then now that we have our value for VF, we can plug that in. We know that the change in y equals VIT plus 1/2 AT squared. VI is 0, so we can cancel that out. Change in y would be negative 10, because that's the distance of the cliff. Be 1/2 negative 9.8 t squared. To solve for d, you would do 10 times 2, 20, divided by negative 9.8 plus t squared, square root both sides. T equals 1.425. Then from there, you can find change in x equals IXT plus 1/2 AT squared. Cancel that out because a is constant. Change in x would equal Vx times t equals 4.62, 1.425. Our change in x would be 6.07. Which is how far it would travel from the base of where it falls to where it lands. And then for part H, a physics student claims that for the same system, if you double the height to 2h, then x will also double. And for this, since we already found our VF, we're going to find our new change in y, which is 1/2 AT squared. So we already established VI is 0. Our new change in y would be negative 20 to equal 1/2 negative 9.8 t squared. Negative 20 equals negative 40. Multiplied by 2 to cancel out the 1/2. Divided by negative 9.8 equal t squared. Square root both sides. T equals 2.02 about. And then we can calculate our new change in x. Again, VIX of t, change in x would be equal 0.62 times our new time, 2.02, our new change in x would be 9.3. Since our old change in x was 6.07 and our new change in x would be 9.3, our distance does not double, which means his claim is incorrect.